Okay, this is going to be the final part, I hope, for this Pearson International A-level exam, Edexcel. It's a physics exam called Unit 1 for covering topics of mechanics and materials. It's the exam taken by last summer the candidates who finished their exam or who were doing AS units at the end of May. Okay, so normally students internationally will take their Unit 1 exam in January, and they'll take their Unit 2 exam along with the practical exam in May. But sometimes students want to retake Unit 1 in May as well. So some of my students did that. So it's the same as making it a linear exam in that you take Units 1, 2 and 3 all in the May sitting. So there are 3 occasions where you can take the international A-level exams. You can take them in January, you can take them in May or June, and you can take them in October. There are 3 chances of doing it, and the content's the same as the Edexcel linear. So if you find these useful, whether you're doing the linear version or you're doing the modular version, please make sure you like, share it with your friends in your own schools, and subscribe so you know when future videos are going to be made. I'm going to do some more over the Christmas period to prepare students to help you prepare for the January modules, and my focus will be mainly on Units 1 for Year 12 and Unit 4 for students in Year 13. Okay, and for students doing the linear, these will be good practice for 50% of the content of your first year. Okay, I will also be adding some linear exams to the website, and I've got one ready, which is the 2022 paper for the paper 1 of the A-level. Okay, so we went through questions 16 and 17 in part 4. It was the boy trying to throw the stone into the tire shown on the water. Okay, and now we're going to go into question 18, and there is a question 19 as well, and question 18 is looking at moments. Now these moments questions, if you've done GCSE or IGCSE physics, it would be in paper 2 of the IGCSE Edexcel exam, and it's not that different to the IGCSE paper 2 questions. So here you have a lorry crossing a bridge, yeah, and it's supported by 2 columns as shown in the diagram. Forces P and Q are representing the forces from the 2 columns at the ends of the bridges. Okay, so these 2 columns are taking the weight of the bridge plus the weight of the lorry in this case, okay, or any vehicles driving across it. So the forces P and Q act on the bridge from the columns. The center of gravity of the bridge is at its center. That's because they are assuming that the bridge is of uniform thickness and uniform density. So its mass or its weight will act from its center of its mass, which is the center of the length between the 2 columns. So at a particular time, the lorry is 35 meters from point X. So that's from support of column X, or the force called P. So we put the P and Q upward forces. We got the weight of the bridge as a downward force at the halfway point, which is 60 meters from force Q and 60 meters from force P, and the lorry, the center of its mass, is at 35 meters from force P. So we're assuming the bridge is at equilibrium, it's not going to collapse. That means we use the principle of moments for equilibrium, where the sum of the clockwise moments about any point must be equal to the sum of the anti-clockwise moments about any point. Now, we choose where to take moments about depending on what the question is asking. So let's go to the question. it says calculate the magnitudes of forces P and Q. Yeah, so we got to do both of them. And it says you should take moments about point X. So taking moments about point X, the sum of the clockwise moments must be equal to the sum of the anti-clockwise moments, which is the principle of moments, and we're doing it about point X as we've been instructed to do. So we know the force of the lorry, yes, or the weight of the lorry, and we know the weight of the bridge. They've given us these values here, okay? We also know that the upward forces, yeah, must be equal to the downward forces. That means P and Q together must, upwards-wise, equal to the weights of the lorry and the weight of the bridge downwards because of the equilibrium of forces, yeah? So that's the balance of forces up and down must be balanced. So if we now take the clockwise moments, and let's look at the diagram, clockwise moments about X. So if we're taking moments about point X, yeah, so we're taking moments from this end of the bridge, the clockwise moments will be due to the lorry and the bridge because they are going clockwise. Then the one that's going anti-clockwise, to balance them, is force Q, okay? So force Q's moment is 120 meters from X, and these, one of them is at 60 meters, yes, the weight of the bridge, and this is at 35 meters. So the moment due to these two, and their distances, obviously, must be clockwise moments must be equal to the anti-clockwise moment due to force Q. Now, by taking moments about point X means we don't have to worry about what force P is. That means we only have one unknown, which is force Q. Okay, hope that makes sense. So once we put the figures in, we know that the force of the lorry at 35 meters, the weight of the lorry times 35 meters, must be equal to the weight of the bridge times 60 meters. That's the clockwise moments. So they are both on the left-hand side of this equation that we're using. And the right-hand side, force Q times its distance from point X, 120 meters, these must be equal. So the only unknown is Q, and you can work out what Q is. That's the force due to Q, which is the column at the far end, will give you a value of 6.12 times 10 to the 5 newtons to 3 significant figures, which is approximately 6.1 times 10 to the 9, 10 to the 5 to 2 significant figures. Once you've got that value in, you also know that P plus Q, upward forces, must be equal to the total downward forces. Therefore, P plus Q, yeah, so if we look at the equation I put initially, I just knew that was going to come. P plus Q must equal that. Now, since we've now worked out what Q is, we can say P is equal to the total downward force minus Q. Okay? So we've put that arrow going all the way down to this equation here. These are the downward forces. Take away the force we've just worked out for Q. Take away the force of Q from it, and you will get the force left for P as 7.88 times 10 to the 5 newtons to 3 significant figures, but you then round it up to 2 significant figures as 7.9 times 10 to the 5, okay? And that's the answer to this section of this question. And then it says, explain why force Q increases as the lorry moves across the bridge. Now, I'm not joking, there's exactly the same level question in GCSE paper 2 I gave recently to my year 10 students. So as the lorry moves towards Q, the distance of lorry from X increases, so the clockwise moment due to the lorry about point X increases, and since the clockwise moments, some of the clockwise moments must be equal to the anti-clockwise moments for equilibrium to be maintained, yeah, due to the principle of moments, you could say, there's your third mark, that the moment anti-clockwise due to Q will need to increase as a result. Since the distance of Q to X is constant, that means the force due to Q must be the factor that increases. So basically, in common sense terms, as the lorry moves more towards column Q takes more of the weight, and column P will take less of the weight, okay? And they're designed to be able to stand a varying force. Hope that makes sense. And really, this is very similar to the GCSE question that my students in GCSE had to do. And you at A level need to be just crystal clear on these type of questions. Once again, practice, practice, practice as many past questions as you can, because they like to try to give you a slight variation on every type of question to see who gets thrown by the variation and who manages to apply their understanding each time. Okay, so that's 10 marks done for question 18, and now we're in the final question. You can see that the later questions take longer to explain and take longer to go through. So here, question 19 is about a zip line, and for those of you who know where I live, a zip line, we have one in JBR. A zip line consists of a cable fixed at 2 points, the lower point and the higher point, and a person hangs from the wire as shown. Yes, they have a harness on them, so they won't be able to fall down. The person hangs from the wire attached to a wheel, which kind of is reducing the friction as they roll down this cable. The cable's under tension. The wheel can move along the cable and hopefully not with too much friction. If there was too much friction, it would slow down. Okay, so in the position shown, the person is accelerating because they are losing height and potential energy is converted into kinetic energy. Okay, now you've got to complete the free body force diagram to show three forces acting on the person in this position. Okay, so I have done it already. The weight of the person is downwards, yes, and the force from the wire, yes, is upwards at an angle, okay? And there must be some air resistance due to the drag as the person is going through, traveling at a certain speed through the air. So as long as you've got the three forces named, yes, you'll get the marks for showing the directions to be approximately accurate, okay? So you've got to get the position of the arrows in the right direction. So question 19, I think this is. So they give you one arrow to the left, it says, and upwards, labeled force from the wire, yes. The other, from the harness. The other arrow vertically labeled weight, acting downwards, yeah, vertically downwards. An arrow to the right showing the air resistance slightly upwards against the direction of travel of the man. Okay, so you get 3 marks, one for each arrow being the approximately the right length. Obviously the weight has to be the greatest, yeah, and the other two must be smaller than the weight. Okay. Then at a particular instant, the tension in the cable, if you measure it, it says it's 1200 newtons, and the angle formed by the cable where the man is making it change angles. Yes, so if you look at the original diagram, you see they're talking about an exaggerated form of this tension here and this tension here, and they've made it look like the angle is more obvious than this diagram, the first diagram. So in this diagram you can see the tension is at a more obvious angle, and they're saying it's 144. So if you add these two vectors together, yes, so you could add the second vector on, you can make a parallelogram of forces, and the resultant of these two tensions will be that the tensions combine to make, yeah, their force in total go in this direction here, F. So the reason is, if you draw a right angle triangle, the component, yeah, so this is a right angle here, you would get one from each side, yeah? And this will be a right angle. And the component of each of these tensions, the one acting this way and the one acting that way, the component of it in the direction shown, which is this way, will be equal to 1200 times cos of half of this angle between them, okay? So it'll be 12 times cos of 72, which gives you a value of approximately 371. So the two tensions, or the tensions times 2, will each produce a component direction of F that I've drawn on this direction here, okay? And so if you add those two, there's two of these, so you've got to double them up, as there are two of these forces, and the force on the wheel will be 2 times this value, 370.8, which gives you a value of approximately 741.6 newtons. That's 4 significant figures, 4 SF, yeah? But we're rounding it up to 740 for 2 SF. Now, did they want us to show anything? No. At a particular lesson, the tension is that, and the angle formed by that thing is shown, and it's not to scale, but you get the idea of the component. Oh yes, we want to show, yeah, we want to show that it's about 740 newtons, which we just did, okay? So again, it's resolving vectors. So resolving vectors could be velocities, could be momentum like we did earlier, or it could be forces, as in this case. So once you know this, there is a force on the wheel from the wire of 800 newtons. That must be the weight of the person. So they're not spelling it out for us. But if you look at the original diagram, yeah, the force due to the wire is the person pulling it down, yes, if you like. And those two tensions that we talked about, the tension was this way and this way. The tensions must be balanced by this 800 newtons that way, yes? So that's what they're talking about, the wire pulling it down at that angle. So the two tensions must be balancing this force on the wire downwards, 800 newtons, which is largely due to the weight of the man or the person. So the force on the wheel downwards, or roughly downwards, I've drawn it as downwards, is 800. The angle between the force from the cable that we just calculated was about 742 newtons to 3 significant figures. And the 840 newtons from the wire is 150 degrees between them. So one is going the way that we showed the two tensions would add up, yes, roughly in that direction. So if you can draw it to scale accurately, yeah, which I didn't have a protractor with me, but if you can draw, I don't know if that's 150 degrees, I was just guessing what 150 degrees is like. So if you draw the 800 newtons, for example, if you have space to draw 8 centimeters down and 7.42 centimeters up, you draw it to scale and you make the angle in between them exactly 150 degrees, you can determine the magnitude of the resultant force, because the resultant force will be this one plus, yeah, it'll be plus the 742 degrees. So it would be, or you could add the 800 newtons downwards. And then when you put them exactly to scale, you can then work out the triangle of forces. Yeah, so if the 800 newtons is added on this way, yeah, you can, if you don't done it to scale, you can then work out what the resultant will be, which will be, this will be the resultant, yeah? Because you've added the 800 newtons onto the 742, yes? So we've ignored, it says you should ignore the weight of the wheel. So I wasn't even going to think about it. Basically, you've been told to add two vectors together, yeah, 742 and 800 at an angle of 150 degrees between them, and you're meant to work it out with a vector diagram. So you've got to draw a scaled vector diagram. That means it's got to be like drawn exactly with the protractor and a ruler to scale. And if you do it accurately, you should be able to get the answer in the mark scheme. I've not tried it, so I'll have to see the mark scheme to see what the scale drawing is expecting you to do. So appropriate trigonometry used, Yes? Yeah, that's for the previous part. So you've drawn the angle, and the resultant force will be similar to the angle I've shown you, yeah? And that you've got the triangle of forces shown. So you get 1 mark for the straight line 8 centimeters long. They want you to use 1 centimeter for every 100 newtons, and show the scale that you're drawing. Then they want you to do the vector addition. So you've changed the situation diagram, so the 800 going down 742 at an angle 150 degrees between them. Then change it into the vector diagram, which would be like this, but drawn to scale. So this should be 8 centimeters down, 7.42 centimeters up, and then you would be able to see what the exact resultant force will be, which will be the third side of that triangle. So once you've got a vector diagram with all 3 arrows, you get your third mark. And then if you can work out that this third side of this triangle is approximately between around 400 newtons. So this, if you do it to scale, should be approximately 400 newtons to the nearest 10 newtons. So they will accept between 390 and 410 if you draw the resultant vector accurately. Sorry, I didn't have my equipment with me at home when I was doing this, okay? But I hope that makes sense, and you can look at the mark scheme to see how they've explained it. And here comes the final part of the exam. The people take turns at moving down along this zip line from the high point to the low point. And the people are initially at rest at the high point. So basically they get their velocity from the potential energy. Now if you look at it, mgh, the potential energy lost becomes the kinetic energy gained. So explain why the speeds of people with different masses are always about the same when they reach the low point. And that's because of the energy transfer. It's like a mechanism that the gravity is doing the work on the person to gain the kinetic energy, and mgh equals half mv squared. You'll notice that the m's cancel, yes, so you don't have to worry about the m's. So therefore the velocity at the bottom end will be equal to the square root of 2gh, yeah? So the v is independent of the mass of the person. So assuming work done against the resistive forces can be ignored, yes, and that a larger person doesn't have a much larger resistive force. We're assuming that, and if that's the case, then the mass doesn't make any difference. It's basically all masses fall at the same rate due to gravity. Okay, so the only thing that could spoil this theory or this idea is that if the resistive forces are different on different sized individuals. Okay, so it's not, remember, physics is a simplification of reality. You can't get 100% accuracy in physics even at advanced level. So that ends the final question of this paper. Hope you found it useful. Once again, please like, share it with your friends. I'm trying to get 1,000 subscribers. I'm up to 600 and something. And subscribe so you know when the next video is uploaded. Okay? Thanks for watching. Bye for now.